In the last video of this lecture, I want to take some of the material we've developed about the semidirect product of two groups and apply it to some first examples that connect back to the examples from the very first video in this lecture. So let's take H to be the group R with plus as the operation. And let's take K to be the group R star with multiplication as the operation. And let's take phi to be a function that takes R star to an automorphism of R that we'll define by saying what it does for each particular x in R star, each particular non-zero x. We're going to have phi x go from R to R, and phi x applied to y will just be x times y. So what do we want? We want this to be a homomorphism from K to aught H. So let's just check that that really is true. We need phi x to be an element of aught H, so to be an automorphism of R plus. Phi x is a bijection from R to R. I mean, x is invertible, like so x inverse is a thing. X inverse exists. And phi of x inverse is a two-sided inverse for phi of x. If you do phi of x and then do phi of x inverse and apply it to y, you just get back y. Same thing if you do it in the other direction. So phi x is a bijection because it has a two-sided inverse. And now we need phi x to be a homomorphism. So what happens when you take phi x and apply it to a plus b? Well, that's x times a plus b, which is x times a plus x times b. So it's phi x of a plus phi x of b. Remember, the operation on the right-hand side here is plus, right? So you can add these. OK, more than just being a function from non-zero elements to automorphisms of R, we need this to be a homomorphism. So what do we need to check? We need to check that phi x1 following phi x2 really is phi x1, x2, the product. And that's easy to check by seeing what does this do to any y. Well, if you apply this to y, you get x1 times x2 times y. If you apply the left-hand side to y, first you get x2 times y, and then you get x1 times x2 times y. So, OK, so this really is a homomorphism from K to aught H. So the semidirect product makes sense. What is it? Well, it has this group operation AB times A prime B prime. Well, that's A times phi B applied to A prime, except remember in the first factor here, the operation is plus. So instead I'll write A plus phi B of A prime, and then B times B prime in the second component. And what is phi B of A prime? Well, that's just B times A prime. So we get A plus B A prime, and then comma B B prime. What is this? So remember from the first video of this lecture, in the affine group over R, what happens when you take x, y, 0, 1, x prime, y prime, 0, 1? What we get is x, x prime, 0, x, y prime, plus y, 1. And if you look at this a little bit, where you match up b, b prime, x, x prime, maybe a plus b, a prime looks kind of like y plus x, y prime, you start to think maybe these groups are connected. So I'm going to pause and erase, and then I'll show you the details of what's going on here. So we have this semidirect product, and we've seen that the group operation looks a lot like the group operation in this affine group over R. This suggests taking a map from the semidirect product to the affine group, where you take a pair AB to a matrix in this group. And the sort of tricky idea is we want to take the pair A comma B to be B A 0, 1. So why is that? Remember, inside the affine group, we have this subgroup H, which is everything of the form 1, 0, 1, something in R. And that group is isomorphic to R. So the first component here, this component corresponding to R plus, should go in the upper right corner where we get this subgroup isomorphic to R plus. And also you check, I mean, BA01, we have this other subgroup K, which is everything of this form, and that's isomorphic to R star with multiplication. That should go here. So really, the pair AB should go to BA01. That's the key thing to remember. And really to emphasize this, I mean, be careful. If you have a matrix in the affine group, you can write it as something in H times something in K, but the order very much matters, right? So XY01 is 1Y01 times X001. But if you switch the order of these two matrices, they don't in general commute with each other. So you have the matrix for Y first, and then the matrix for X. That's the way to remember it. Okay, what happens when you conjugate something in H by something in K? I claim that this conjugation looks like this phi k h comma 1 that we get when we conjugate inside a semidirect product something in H tilde by something in K tilde. And you can just check. X001 times 1y01, x001 inverse. We get 1 xy01, which is 1 phi x of y01. So what is this corresponding to? This is if you take A equal phi x of y and B to be the identity 1 in R star. So what we're seeing here is this semidirect product and this matrix group are really closely related. And in fact, this map phi really is an isomorphism. All of the pieces are here, and I will leave it as a little exercise for you to check the final details. So I'm going to pause and erase, and then I'll talk about one other very, very similar example where we have an affine group not over R, but over a finite set. Let's talk about a final example. Let's say that H is Z mod MZ with plus as the operation. M is just some positive integer. And K is going to be Z mod MZ cross with multiplication as the operation. So really to emphasize, this isn't non-zero elements mod M, it's invertible elements mod M. So this is an abelian group of order phi of M, where phi is the Euler phi function. All right, so we know what's the automorphism group of H? It's isomorphic to Z mod MZ cross, same thing. So invertible elements with multiplication. Let's define a function from K to aught H where, okay, for any A in Z mod MZ star, we let phi A go from Z mod MZ plus to Z mod MZ plus by sending phi A of X is going to be A times X. So we're going to take in an element of K and output an automorphism of H. Okay, so let's check that this really is an automorphism. So phi A is a bijection since A is invertible mod M. So that means A inverse really does exist mod M, the multiplicative inverse of A mod M. And phi A inverse is a two-sided inverse for phi of A, for phi A. That's easy to check. So that makes it a bijection. And phi A applied to X plus Y, I mean, it needs to be a homomorphism from Z mod MZ plus to Z mod MZ plus, is AX plus AY. So that's phi A of X plus phi A of Y. Okay, so each phi A really is an automorphism. And this isn't just a map from K to the set of automorphisms, but it's actually a homomorphism. So it's easy to check that phi A following phi B is phi AB. This is very, very similar to what we did in the last example. Okay, so the semidirect product of Z mod MZ, where the operation is plus, determined by phi A or with respect to phi A, the semidirect product of Z mod MZ plus and Z mod MZ star with respect to this phi A is isomorphic to this affine group where the entries are now in Z mod MZ. So, okay, when we first talked about the affine group, we talked about the affine group with entries in a field F. But this still is going to make sense Like you can check that now we want the elements in the upper left entry of our matrix to be invertible in Z mod MZ. So not only do we want the determinant of such a matrix to be non-zero, but we actually want it to be a unit in Z mod MZ. Sorry, an invertible element modulo M. So what is this isomorphism? We're going to take the pair A in Z mod MZ, B in Z mod MZ star, the invertible elements modulo M, to the matrix BA01, where B is going to be in Z mod MZ star, and A is just anything in Z mod MZ. So again, just emphasizing, you can write this as a product where the matrix corresponding to the upper right entry comes first, 1A01, and then B001. So I will leave the details of checking that this actually is an isomorphism to you.